start recording? Yes, it's recording. Okay. Yeah, so welcome to discussion 7. We are going to, or 8, sorry, discussion 8. We're going to be talking about pipelining and hazards today. I know we just covered caches, but caches discussion is this week for regular discussions, and then next month. I just realized next Monday is break. We'll figure out what to do about that. But hypothetically next Monday for this course, or sorry, this discussion. But yeah, so just getting into things, how we're going to break down today is basically we're going to do a pipelining review, a hazards review, and then jump straight into the worksheet, because with kind of things like this, it's much easier just to go directly in and do practice, because a lot of the questions on exams will be like identifying hazards, kind of like figuring out how things are pipelined and things. And so the theory is like still very much similar from data path. So yeah, getting started, pipelining. What is it? Well, okay, so pipelining, it helps maximize efficiency. So when we go through the regular data path, oh, by the way, if you need worksheets, they are up here, the paper ones. So when we look at the data path, one of the things that we identified in lecture that was really not great is only one instruction can pass through at a time. And that was kind of an issue, mostly because we had this whole problem of like, okay, well, if I'm doing stuff, like if I'm fetching an instruction, all the rest of the components just sit there and they don't really do anything. That doesn't mean no signals are being passed to them, because it's still actively like there's actively no signal or actively old signals. It's just they're not being processed. So the idea of pipelining the data path is kind of like taking advantage of things that don't have to run concurrently and can theoretically, in theory, run parallel to each other, and to use and apply them to different instructions. So the maximum possible efficiency in an n-stage pipeline, so in our case, n being 5, is going to be n instructions in the pipeline. So one unique instruction per section. But in reality, it's not actually going to hit that. In lecture, we saw that a common CPI for or cycles per instruction taken is not going to be the highest possible, but rather it's going, or sorry, instructions, the number of instructions, sorry, the throughput is not necessarily going to be 5. So the efficiency is not going to hit that end, and rather it's going to be a lot lower. And the reason for that is just because even if you add this kind of pipelining, you need to add extra hardware, there's extra computation time, and there are things that have to wait on other things. And so eventually it kind of still brings it back down. And so that's what we're going to try and address. So the standard 5-stage pipeline is based off of the different sections that we talked about last week. And so just as a review, IF is instruction fetch. Sometimes you'll see that as just denoted as F. ID is instruction decode, sometimes used as D. EX is execute, sometimes just as X or sometimes E. And then mem is the memory access, so read on default, write when marked as such. And that's usually written as M, and then write back or W. And that's the part that writes back to the register file. If you need a paper worksheet, there are ones over here. So how is this implemented in real life? Because in theory, if we actually just pass a bunch of instructions in, it's not actually going to do what it needs to do. And the reason is because if we look at the data path, a whole bunch of it is just wires, and we count wires as being just negligible time. So it's not going to actually slow down the instruction. And so it's going to like start overriding other things, and they kind of all just bleed into each other. Not to mention like the clock cycle will be all like messed up, because we have to follow the clock cycle of the old data path, but that means like we can't load the instructions, and so it just doesn't do what we need it to do. So what we do here is we add a register for every wire carrying a value when the stage is changed in order to do this. So the whole idea of first like adding a register, that purpose is basically to maintain the previous stage's value in order for the next stage to be able to actively use it, even while a new instruction is being passed in, because registers hold values, right? And so the kind of for every wire carrying a value when stage is changed, that exists because when we have wires that pass from stage to stage, we know it's going to be used at some point later down the line, but we don't know when. So we want to make sure if say a wire is like being carried all the way from decode all the way to write back, we want to make sure there's a register at every single stage, keeping that value consistent and being passed like along like register to register, even if it's not going to be used in the other intermediate stages. So you can kind of think about this as like, for example, like I was gonna say conga line, but that doesn't really, like, if you, I don't know, are like in a pipeline in real life, when you're like maybe packing something or like an assembly line, like one person is in charge of doing something. Once they're done with that, they pass it on, and then they receive a new thing. And so that's the same kind of way that it works here. Worksheets are up here. Out of curiosity, how many people here are in 16B? Okay, that's what I thought. The 16B midterms tonight. So everyone, I think, who's in 16B hasn't shown up for anything today, which makes sense. Yeah, no, which is totally understandable. I also skip things when I have midterms. But yeah, if we kind of take a look at this is what a kind of a pipeline diagram would look like. So the pinkish red lines kind of denote the different stages. And you'll notice that this is really different from, or okay, not really different, but like considerably different from our normal data path. And so let me see if turning on pointer will help, because kind of laggy. But you'll notice that like, we have all our typical structures. So we have like the +4 for the program counter. Here we have like the muxes. All of these things have pretty much stayed the same. But like right after every line, we have like all of these extra registers. So we have a whole bunch more registers and hardware than we did before. So we see we have a program counter with subscript C. I don't know if you can see it really clearly, but I'll go through each of the registers. So the program counter with a D, it kind of keeps the program counter for that particular instruction that just got loaded and passed into the decode section. And the reason that we want to keep this is because at some points we'll want to have PC +4 being written back to say the return or RA register. So we do need that value even if we're not actively using the PC to index memory at that point. So you can see that like we have PCD, PCX, PCM, and then PC +4 right back. So it's just another register for that. And so we see that we got the +4 adder here. So if you remember from last week, I did mention that we could pass the +4 value all the way down. We could also pass just the PC value all the way down. And you can see here, the reason that it's kind of usually done this way instead of the way that I talked about last week as an alternative is because when you have a pipeline diagram, we're going to use only the value in the pipeline diagram or in the register. As opposed to last week, we can kind of split things off. But here we can see that like we use the PCX value to go into the ALU because PC offset memory addresses need to use that. And so carrying two values over here, like both the PC and the PC +4 value is just, I guess, less efficient because then you would need another extra register here to carry PC and PC +4. And that's just extra hardware. So instead, we just put an adder later on. So that way we can do the calculation later again. And then similarly, we have like an instruction decode and that gets eventually decoded down here. So you notice that I didn't include the control logic, and that's just because the control logic pretty much stays the same, and they're determined by basically the control kind of registers. So you don't break down the instructions every time you're in a new stage anymore, because you could do that, but that would be slightly inefficient because you would have to revisit control logic, re-go through, hash through all the calculations every single time. So instead, it all gets decoded in instruction decode, hence why we have instruction D here. We get decoded somewhere down here, and then the control bits get kind of saved to a register here. So we know from last discussion and from lecture that we don't have that many control bits. We have enough that can all fit inside a register. And so eventually what can happen is at like different positions in the register, so maybe at like index bit 0, 1, etc., all the way down, you set the bits that you need in order to be read off later. And so that gets passed down stage to stage. Are there any questions so far? Bless you. Yeah, decode takes the instruction that you just fetched from instruction memory and then kind of breaks it down to get all the control signals like, for example, read register and, or sorry, write register enable, register write enable, sorry. And then like the immediate selector, the branch comparator bits, all of those things. So the idea of a pipeline is basically like we have instruction 1 that gets passed into the very first stage. And so one thing to note is the clock cycle will now change. It's now timed according to the longest stage in here. So previously we know that like the clock cycle is based off of the maximum instruction that passes through the entire data path, so load word. But now instead what it is we find the longest section here because it has to be timed according to the longest stage. And so that stage is usually execute or it's usually memory. And so you would want to calculate the critical path of every section. So we have exercises for that in the worksheet. And so what happens is at each new clock cycle, a new instruction gets passed in, unless there's some really obvious reason not to. So we'll talk about that later. So assuming that like everything just like there's one new instruction per cycle. So cycle 0, instruction 0 gets passed in. Cycle 1, instruction 0 gets passed to here. So the bits that are needed, so PCD, and then the instruction itself gets passed in here. And then we load the next instruction, so instruction 1. And then so at the next clock cycle, then the stuff that was here, so instruction 0 now gets passed over here. It has all of the values that just got broken down. And so it can do whatever it needs and execute the next instruction. So instruction 1 now gets decoded. And then instruction 2 is what's now fetched from memory. And so on and so forth until the pipeline is completely filled. So until instruction 0 is in this stage technically, even if it doesn't need to go through right back. And so at that point, we would have instruction 0 stuff here, 1 here, 2 here, 3 here, and then 4 just fetched. Does that make sense? Okay. Yeah, so oops, that one's slightly offset, I guess. So the reason for that is because, okay, so if we go through here, we know that we use PC first to address instruction memory. So that's like done in instruction fetch. And then we need PC later on because there are PC relative memory addresses, right? There are also absolute memory addresses or 0 relative. So like PC is used for things that usually include labels, so like JAL and branch instructions. And so we need the PC in order to calculate like where the instruction or the label actually is to be able to replace it later on and to be able to actually access that instruction. And so we need PC plus offset. And so that's done in the ALU section. So we get our PC from here, and then we get our offset from the immediate generator passed through here, and then the ALU adds them together before passing it to the ALU output. So that's one of the reasons. And then does that make sense?
Essentially, like, you know how like you're saying like each of like the cycles like the right.
Yeah, so the PC, what gets passed in, so at this point, so let's pretend this doesn't exist for now. So this would just be PC right back. And so this would include the program counter for what the first instruction was. So where that is, and then this would be theoretically hold the next one. So the PC plus 4, this would be PC plus 8, this would be PC plus 12. So it's each subsequent instruction. The main difference between like what's shown in reality is like the second reason that we would use the PC, and that's for when we're trying to calculate a return value. So PC plus 4 is the return address that we would theoretically sometimes want to write back, so to the RA register. And so that's why it gets passed along here. We can see it being actively used in this path. And then we can also see it being actively changed here before it gets written back. Does that make sense? Are there any other questions? Okay. So how does this affect timing? We already talked about this a little bit, but we can see that in a non-pipeline clock cycle, it's the critical path of the entire data path. So again, load word. So sorry if I'm rehashing this too much. It's because it's pretty important to understand why things change. And then the pipeline clock cycle is the maximum of the critical path of every stage. So like I said before, it would be execute or the DMEM access. And the reason is just because ALU, since it's so complicated, often takes a considerable amount of time. And then DMM, because it's usually main memory. We did talk about caches a little bit, but I'll just kind of add that on. So like sometimes like when we access DMEM, it's like the process of first accessing cache. If it's not there, then we access main memory. And main memory is considered DRAM, which is dynamic random access memory. And that's just kind of slow to access because of the way that it's built. So DRAM is built with like, transistors and capacitors. And capacitors like need some time to charge. Sorry to ruin your guys' day with EE stuff. But because it has both of them, transistors are really fast. That's why registers are so fast, because they're primarily built out of those. But capacitors, because they take time to charge, that's how they actually like store memory. So like it's kind of really nebulous here. We don't really care about how exactly it does it, but because they use capacitors, it takes longer to be able to access that and to be able to get something useful. And so that's why the main memory is slower than than that. And because when we add the cache access on top of it, usually like this section is typically pretty darn slow as well. Yeah. Mhm. Yeah, so registers are typically built out of transistors and are on chip. DMEM is just data memory. DRAM, the DRAM is dynamic random access memory. Caches are, Yeah, so that's typically like what we consider main memory to be. Caches, which we first introduced on Thursday and we'll be talking about tomorrow and this upcoming Thursday as well. They're made out of SRAM, which is static random access memory. And they're built out of like a really unique configuration of transistors, which is why they're like fundamentally faster than main memory. But yeah, this is all like out of the scope of this discussion, but kind of that's why it contributes to the latency. Are there any questions for this? So yeah, fundamentally, we know that the pipeline clock cycle is going to be faster usually than the non-pipeline clock cycle. If it's not, probably mean there's something else going on. I have no idea why it would be longer. But yeah, if you calculate in your problem and you're like, oh yeah, the pipeline clock cycle seems to be slower than the non-pipeline clock cycle, I would redo your math because that probably shouldn't be the case. But something to note, I guess, in this whole thing. So when we did the non-pipeline clock cycle, the clock cycle you would calculate, okay, so this is the first register that you kind of access. And then the last register you kind of access is the reg file right back, because we want to include that as well because load word does. We didn't get to it last discussion, but I'll just kind of briefly talk about it. So when we hit the different components, so we would first hit the program counter. So we would want the setup time for that as well, or the clock to queue time for that so we can actually get the output. And then we would want the access time for IMEM. We don't care about the time that it takes to do the adder because it happens at the same time. And accessing instruction memory is going to be a lot slower. Skipping over these registers because we're talking about non-pipeline for now, then we access the register file and the time that it takes to read the register, aka more clock to queue time, is going to be factored in. And it's going to be the max between that and the immediate generator because immediate generator happens at the same time as the reg file reads. And then so jumping onto the execute stage, then we want to take the time that it takes for these muxes to select the right values as well as the ALU time, and those two added together. So only one of the muxes need to be added to this because these two muxes happen at the same time. And so we don't consider the branch comparators time. You'll usually be given it as a distractor, but you don't care about that because ALU computation plus one mux's time is going to be a lot longer than it takes to compare 32 bits. And then we want to add the DMEM write time or read time, whichever one's longer, because we want for load word, it's going to be read. And you won't have a longer clock cycle than that. And then for the last one, we want to add another mux because we have this one in parallel with our write back here. And so that's going to write back to the reg file eventually. And so that's what constitutes a critical path of the entire data path. But for the pipeline clock cycle, we want to look at each one individually. So like all the stages that we kind of jumped through, they're all going to be in individual critical paths now. But what we do add on is we want the clock to queue time of the registers in between all of these. So that's what we'll be looking at in the kind of clock cycle calculations in the worksheet today. Does that make sense? Yeah, so pipeline takes everything individually. So you will have to calculate through all of them in theory. In reality, like you would only need to take the max of these two, but given the parameters on an exam or a homework, like for some reason, this might take just super long. So you do want to go through and calculate everything. Yeah. Okay, so just going through, this is just some general question styles because I think this, I guess, data path and pipelining questions, there is kind of some creativity that goes through. If you look at, I would say like the spring and summer 2021 exams, especially the spring 21, like it looks pretty different. Some like questions you might be like, oh yeah, if the data path like looked different, how would this affect things? But some pretty standard ones are like, if you're given these specific times for each component, is the pipelining scheme valid? AKA, does it obey timing conventions? And if, say, you want to implement an instruction, what needs to be changed? For example, if we need to do something that like has a new immediate, like it has an immediate, like 17 bits of immediate, we would need to change control logic, and we would need to add another control signal to the immediate generator. And those would be the two main changes that we would have. So it's kind of understand. That's why I mentioned like when we're doing the instruction breakdown that like you don't need to memorize things, but understanding like fundamentally why like certain parts of the instruction are incorporated into the data path and how they affect like the behavior is kind of important. And then a pretty common question is like no op and stall count. Like, so no op is no operation, and it's basically when you just want to like not load a new instruction into the data path or into the pipeline data path. So that would exist for things like, for example, certain types of hazards that we'll talk about in a few slides. And then, so these questions are all kind of like, or this question is just about hazards. It's very, very standard. I would say last fall had, I think, or fall 20 had a question on it. Spring 21 definitely did. I think summer 21 did as well. I haven't looked at last semester's exam, so I don't know. Cycles per instruction is also one. So, and then instruction signals is also another one. So this would be just general data path and pipelining questions. So nothing like super out of the park there, I would say. But yeah. So now talking about hazards. So what hazards are dependencies that affect our outputs? So a question was asked in lecture at some point, was like, well, like if we have an add to a specific register that we want to use in the next instruction, how would we deal with that? Because if we look at our kind of our pipeline over here, we know that a big kind of issue is the fact that like we only write back in the fifth stage. So our instruction 0 is here. Say like we're writing back to say register T0. But say instruction 1 needed T0 at some point for like whatever reason, maybe it was an address, whatever, we don't really know. And it needed the new value of T0 because like we always kind of assume that the next instruction relies on the value that previous instructions have changed. But the problem is the decoding has happened here already. We've already decoded, so T0 corresponds to whatever register in the reg file, and then we've outputted the data already to one of these two registers. And then from then on, we can see that like it just does not change. Like it can't go back and say, let me reread the reg file value. So then what would happen is instruction 1 would then rely on the wrong value of T0. And so the add that just happened here, in theory, is now kind of rendered moot because it never actually got kind of like perpetuated here. So that is one of the common dependencies that you'll see. So hazards always prevent the next or any future instructions from either completing with expected behavior if they start. So like the example that we just saw, it got started, but we are using the wrong T0 value, or from actually even starting in the next clock cycle. So the difference between these two is the first one is we're just going to have all instructions execute and go in the pipeline, even though we know that there might be problems. And the second one just says, okay, well, I know there might be problems, so I'm going to try to prevent those problems by just like stopping the pipeline. And both of them have issues. Like this one keeps the cycles per instruction good, but we might have bad data and just garbage stuff that we don't know. And then this one like severely impedes the cycles per instruction, basically gets rid of the whole pipeline structure to begin with. Because like say if instruction 1 needed to wait until instruction 0 was done, then we effectively don't have a pipeline, right? Yes. So the second one is either no ops or stalling. They're slightly different. But so stalls, okay. So I think no operations are actual like software stalls, and then stalls themselves like can be like technically built into the hardware. So the difference is kind of like slight, but one is like a hardware version of it, one is a software version. And they both like eventually do the same thing. It's just sometimes like it's more optimal to use one. Out of scope of this class, but sometimes it's more optimal to use one just because of the hardware that you're given or the behavior of certain software. So this is plug for 152 to get into that. But yeah, so starting in the preventing from starting in the next clock cycle is basically putting a pause on instruction. And so it's inserting like a bubble or whatever you want to call it out of the many names that you have and say, okay, I'm just going to hit pause, pause, pause until I know that something's correct. So you can see like how that would delay everything else and it might slow down the entire pipeline. So we have three main kind of hazards. So the first one is a structural hazard, and it's caused by the same piece of hardware being accessed by more instructions than their access points. So it's kind of a very like broad definition of things. But if we go to the reg file, let's go back. I think it was this slide. Nope, that was my skipped slide. So if we go back to this and we say, okay, well, we see we have IMEM and DMEM here. This whole time we've just been talking about it as if it's one continuous piece of memory. So like we know code is at the bottom, so that's technically IMEM, and then the rest of it's DMEM. And so if we kind of just mush these two together and we have one input, so the address, and then one output for whatever result there is, and then maybe like control signals, you can see that you can only have one access at a time. So only either in a PC kind of address or a data kind of address can insert or can go inside memory and like read it at the same time, because we just don't have the support for like other wires to go in. And so that can cause an issue, because then we're like, okay, well, if something's kind of fetching stuff here, then we have to just sit and wait until it's done. And then so that might cause issues, because then we would have to like, okay, like we fetch it for IMEM, and then we wait on DMEM, and then we have to fetch for DMEM, and then wait for everything else before we can move on. And so that's why like we already have solved a lot of the structural hazards because of this very issue. So like we can see, that's why we split them into two separate ones. In reality, sometimes on chips, like you'll have two separate like actual memories for that. Sometimes you'll have one, but there's just different entry points, so they're effectively thought of as both. But we've already solved that one. A separate one that you might like notice is the reg file. So we can see that the reg file has like a bunch of different inputs and then two separate outputs. And so what this is doing is, well, if we only had one input, so like for example, adder D or data D or whatever, we would have to wait multiple clock cycles to be able to like access different registers. So we would have to wait until register A is done for source one. Okay, it read whatever was in register A and then outputted it. Now we have to read what is in source register 2 or B and then output that before we can go back and say, okay, I need to index this data register, and then that's before, and then I might not even be able to write into the reg file if we only have one input, because we don't have all of that. And so you can see that's been resolved by just having multiple buses so buses is a term that basically carries data or values into a piece of hardware. And so that's why we have multiple buses in and out of the reg file for that very reason. That makes sense? So yeah, structural hazards are typically not seen as much. Can anyone identify a potential structural hazard that we haven't resolved yet at this point? Like that we haven't talked about a resolution for? So we know we've already identified the IMEM DMEM kind of, I thought I skipped this. But the IMEM DMEM kind of a thing, and we also identified like during the decoding stage accessing multiple things. What is a potential structural hazard that still exists? Yeah. Current comparator. Why is that? Yeah, so that one we only need for one instruction at a time, so that is technically okay. So think about like right now we've looked at things that happen in one stage, we've looked at things that happen in two stages. Is there anything else that gets accessed possibly in two stages at the same time? I'll give you a hint. Look at the write back stage. So now you can see we have a register there, and it's unique to that write back stage. But what is write back going to? Or rather, where is write back pointing to? Reg file, right? But that's happening during write back stage. What other stage also accesses reg file? Yeah, so instruction decode. So we can see that like we do have the support for that. So we see that adder D and data D kind of come from the write back stage, or adder D doesn't really, but data D does. And so they come from different stages and might be accessing or trying to access things at the same time as the decode stage. And that could possibly cause an issue. And that is both considered like kind of like a structural hazard, I guess, but also a data hazard, which is the next one. And the reason is just because, say if we read from this before we actually write to it, then say if we're like, say we read from T0 and then we only write to T0 in the next stage, and that would cause like a problem earlier because we have a weird dependency that like hasn't actually updated anything. And not to mention that like when two stages try to access the same piece of hardware at once, it'll possibly violate some timing conventions. And so there is actually a solution to that. It's called this idea of double pumping, which is basically doing two register operations. Because remember, all of these things in here are register operations and can only be read to or read from, or written to and read from in one clock cycle at a time. So if we try to do both actions at the same time, it's not going to work. So that's when the idea of double pumping kind of comes into play, which is just two register operations per clock cycle. Ooh, we do have like a solution for that. But the way that it kind of generally works is like we do some things timed to the rising clock edge and we do some things timed to the falling clock edge. This is not something that you'll have to calculate, but it is a term that will show up on either exams or your worksheets. And so like we can have maybe like read combinations, we can have read-write combinations, and we can have write and then read combinations. So basically what that means is on the rising clock edge, do operation A. On the falling clock edge, do operation B. So A is going to always come before B. So if we have two read operations at the same time, is that okay? Will it ever cause any issues? Yeah, so that's fine. If we have a write and then a read, will that cause an issue? Sometimes, right? Because if we want to like read a previous value, so the whole write and read thing is like in theory it could cause an issue, but the way that we kind of sidestep at that is basically saying, well, if an instruction A comes before instruction B, we're going to assume if they use the same register, instruction B's value will rely on whatever was changed in instruction A. Otherwise, you as a programmer has done a dum-dum. Like we should swap the two instructions then. So if we have a write and then a read, it means instruction A's write is supposed to come before instruction B's read. And so that's usually going to be okay. But the issue that can sometimes come is if you have a read and then a write. And the reason for that is because we might come across the kind of issue where, well, instruction A is supposed to write, instruction B is supposed to read. But if the read comes before the write for some reason, just because of maybe the way that things were scheduled or timed, then it could cause an issue because you're, again, reading something before it's been updated. So this is, as far as I think I'll get into that, more about that will come in 152, but it's just a general kind of look into why like this happens. Does that make sense? Okay, so typically what you'll see on worksheets, it'll say maybe like double pumping is allowed. Usually that's referring to, okay, I'm going to write what I need from the write back stage before the instruction decode stage reads from that same register. So it's usually making that assumption. I would say if it doesn't specify or if you're not sure, you can always get a clarification on that. The assumption is if like say a problem says, oh, assume double pumping is enabled, it means that like say instruction A here and instruction B here, it means that A is going to write to the register in the reg file before the instruction decode reads from that same register. So that ensures that we have updated value. Yeah, it's because of the original reason that like registers only have like the input D and then the output Q, right? And so you can't have two separate instructions attempting to access and change that register at once. So if write back is trying to happen and then the read from the instruction decode is also trying to happen, then you have two conflicting instructions trying to access that same register. So that would cause a structural hazard. And then the solution for that is like creating the idea of double pumping. So timing to rising clock edge and falling clock edge. Does that make sense? Okay. So yeah, if any of that is confusing, that's totally okay. Hazards are a bit of a weird kind of thing. We'll go through some examples later. So the second type of hazard, which is probably the most likely one that you'll see, basically if something's not the third hazard, it's typically that we haven't talked about yet, it's going to be this hazard. This is the most common one, and it's caused because data that's needed by the following instruction or instructions afterwards is needed before it's properly updated in the corresponding piece of hardware. So this includes, like, for example, maybe storing to memory is another like update. that may not happen in time. Or if you, for example, are writing back to the reg file and something hasn't been updated either. Yes?
That's the problem.
I-
If it's updated.
Yeah. So it's it's not likely to be the case that like you're updating something before it's being read inappropriately, because if you're at the write back stage, it means that instructions should have come before, like in your program sequentially, before that instruction is attempting to read it in the decode stage. So it's always should be in order. Yeah. And if it's not, and you're like, oh wait, the value is wrong, then you flip your code, basically. So data hazards are really, really common. It's a kind of a dependency thing, because like we'll sometimes be like, oh yeah, we'll bump the what's it called, like counter by 4 or whatever, and then you like try to use it on the very next cycle, but if it's pipeline, then like it won't have been updated yet. So we'll see some examples of that later. And then control hazards. So this is caused when you have a flow of execution that has more than one option due to branching or jumping. So one of the kind of things is, well, in JAL or JALR instructions, that automatically already causes an issue, even if it's unconditional branching, basically. And so what happens there is, well, if you are executing JAL, one line below, it's going to already be loaded into the pipeline, but the jump is probably not going to go to the very next line. It might be, and you'll be okay, but it's not guaranteed to be. And so if you make that assumption, then the instructions that get loaded into the pipeline right after that jump instruction or that branch instruction are going to be executed, and you'll run into a problem, because then you'll be updating registers or memory that you're not supposed to. And so that might cause unexpected values. Similarly for branching, because branching, we have two options. You might execute the next line. You also might not. If you do execute the next line because you didn't branch, that's okay. But if you do eventually branch and you still have the next few lines loaded into the pipeline, that's going to cause a control hazard, because you have wrong instructions in the pipeline. Does that make sense? Okay. So going through them. So again, I'll speed through the structural one just because we talked about it a lot already, but common situations, the memory array and the reg file, we've already kind of solved it. So hardware is separate into instruction memory and data memory. And then we add multiple buses and ports to the reg file to allow for different and multiple accesses at the same time. And for registers in particular, double pumping. So read, write, or write, read. So the official definition, again, is two register operations from separate instructions during one clock cycle. And so this kind of like, it feels like, oh yeah, it violates SDS like timing conventions and stuff. It's not, it's just a slightly more complex version. And we're not going to be talking about the specifics of timing there, just because it gets a little complicated. So, okay. Software solutions, if we didn't want to do that, we could just stall. We could put no operations in there. This would just incredibly slow down the pipeline a lot and probably block it up, and it just makes the pipeline unusable. And a data hazard. So writing to a register prior to an instruction reading from that same register. And so an example of this is, for example, if you have add T0, X0, 5, we're supposed to have 5 in T0, but that only happens when write back happens, which is on the 5th stage. But then we have the shift left, depending on that value that should have been a 5, but probably is not a 5, by 2. And the value gets read from the reg file during the decode stage, and we can see that that happens before write back. So that's the issue. So the solution is stall or no op. So we could technically bump this by, say, 1, 2, 3 stages. So instruction decode happens after write back. So that would be 3 stalls, or we could forward. So what forwarding is basically saying, okay, well, after execute, we already have what we need. Like write back is only really a formality to update the proper hardware, but we already have our solution that we need after execute stage. And we don't care if we get a wrong value at decode, as long as we have the right value during the execute stage for the next instruction. So instead, what's going to happen is it's say, okay, Well, at the very end of the execute stage, before I pass it on to the next clock cycle, I'm going to take that value and basically connect it, conditionally connect it to the start of execute for the next clock cycle. And so eventually, well, during decode, we're going to have decoded the wrong value for T0. It might be some random thing, but we don't care because we're not going to use that value, and we're instead going to use conditionally use the output of execute from the previous instruction. So that's what forwarding is. Yeah. Are there any questions? Yes. To something.
Yeah.
Yeah, that's a great question. So I would say you would, if we looked at the actual pipeline over here, let me bring it back. So if we looked at this, we see that the data that gets written to is only really needed at like DMEM. Like we could technically forward it to the end of like this, but that stage happens before our execute for the previous instruction is finished. So instead it would forward to basically data write or whatever you're trying to write here at the start of mem. So yes, you could also forward that. So, but that also leads to a really good question or a really interesting topic kind of surrounding the concept of memory accesses. So data hazards also kind of exist in the mem stage because, well, if we're reading from DMEM and we're loading it into a particular register, we're still updating that register and we still need that value for the next instruction. So it's the same thing as execute, just one kind of step below. So an example of this would be, for example, like if we have a load word, we're only actually going to be able to fetch the value after the memory stage, but we need it by the next execute stage. So like here, we need to load it into T0, and we need T0 when we're doing at. So it needs to look something like this, but why is this wrong? Or why would this not work? So if we look at our previous forwarding, it looks like this. So it's the next stage. But if we look at what happens here, the direction of the arrow, is it pointing in the same way? Yeah, so it's pointing left or almost backwards, whereas the previous one was pointing forward. So even though this kind of looks still to be okay, it's actually not. And the reason is because we have the output of here, we're depending on something that's read to the output or loaded to the output on the same stage. So execute needs whatever mem is outputting, but these two occur on the same stage. So it's almost like we have to rewind time in order to be able to do that. So that wouldn't actually work. So if any of your arrows kind of like point backwards like that, or point from the end of one stage to the beginning of the next stage, and those two stages are happening at the same clock cycle, it won't work because you're relying on something that hasn't actually been calculated or read from yet. So that's why we would only work for every other instruction. And the reason for that is because say if we have, we decided to just insert another operation in here, maybe it's not a no op, maybe it is, but if we do have another operation in there, then this instruction pipeline is going to be bumped one more to the right. And so we would have instruction fetch, instruction decode, execute right here. And so we could forward from memory to execute over here. That makes sense? Yeah, because right here, memory and execute are happening at the same time. They're happening simultaneously, just for different instructions. And so it wouldn't make sense to be like, okay, now I'm going to rewind, forget everything that happened just in the current execute stage, and then forward it backwards, because that's, again, delaying the pipeline. And so in theory, what you could do is if you have code that you can restructure, maybe you have like another add instruction that doesn't rely on T0. You could insert it right here. And so that way, this one would happen one instruction later, and then you could forward the result from memory to where execute would be now right here instead. Does that make sense? Okay, if it helps, I can also annotate. I just need to reshare, I think. I think it worked. Let me double check. Yes. Yes. So your CPU for project 3 will be eventually pipelined. And you'll also need to implement forwarding. Yeah. So that's why, okay, so 3A is you do the ALU, you do the reg file, and you do just add, I think, as an instruction, or it was add I, one of the two. And that's something that you can hard code. And then in part 2B is where you do the control logic, which is one of the biggest parts of it, the heaviest parts, and then you'll also implement pipelining and forwarding. So what I mean is, like, for example, you see that? No, you cannot. Okay, hold on. Let me try and exit. No. I'm gonna try to just entirely reshare. Whatever. Am I like, oh no, that's not what I wanted. Maybe if I just share my entire screen, that would work. Okay. So if I so, okay, let's try this. So if we have something that exists like use the other instruction from earlier. So like 2, 2, 1 by like 3. If we have something like this, then we would have, okay, the instruction fetch stage here, and then we would have decode here, execute Marie, and then we would have right back here. And then for our new kind of whole deal, so that one. So it would no longer be this. So instead for our add instruction, what our pipeline would look like would be we would have, okay, instruction fetch here, and then decode here, here, right here, and then right back in the swap stage. So timing wise, we have cycle 0, 1, 2, 3, 4, 5, 6. And so what instead would happen is, okay, so now you can forward it basically from, let's see, okay, the output of mem here to the beginning of mem or execute right here. And we can see that it goes quote unquote forward in time because these are now two separate stages. And the second one is like more in the future. So we don't have to rely on something that's already happened. Does that make sense? Yeah, the reason for the originally also pointed to execute. It's just that this like literally just physically cannot happen. Yeah, so this is kind of like illegal because, well, memory and execute are happening at the same time. So we can't feasibly take the output of memory and then pass it to the beginning of execute because execute has already happened by the time that memory also loads. Good on that? Okay. It'll become more clear when we look at actual code. Get rid of that. I'm like low-key struggling here. Let me like see if I can just spotlight. There we go. Okay. Hello. Hello, it's me. Okay, so for the control hazard, common situations like we talked about are jumps and branches. We don't know what instruction we need to execute afterwards. Even for JAL instructions or JALR, we know in theory as a human like where we want to jump to, but as code like we just don't because it hasn't yet like updated all of that. And so for example, like if we have something like this, we have branch equals x1. So we're checking if x1 is equal to x2. And if they're equal, then we jump to label. Otherwise, we're going to do this next instruction. But if we just load the pipeline, we're going to load add I and then only realize by the execute stage that, oh, wait, maybe these two aren't, or they are equal. And if they are equal, then we wanted to branch. So we wanted to do the other stuff instead of do this. But at that point, it's too late because add I has already been loaded. Does it make sense why, or can you tell me why, like by the end of execute stage, we already know where our next instruction is going to be? Yeah, so that's one of the reasons. Yeah, exactly. So we know from the branch comparator, which happens during the execute state, whether or not we actually do branch. And so that changes the control logic. And if, well, we do need to branch, then we have the output from the ALU based off of the PC plus the offset that we can now jump to and update in the program counter. So after execute stage is when the branches have been resolved. So solutions, we can also stall. So we can basically stall until the end of the execute stage for that branch instruction. So we could theoretically say, okay, we'll branch, we're going to go through fetch, we're going to go through decode, we're going to finish execute, and then we're going to load the next instruction. So we're going to have 3 stalls in that case. But again, like that slows things down, and we don't really like that. So instead, what we decided to devote an entire branch of research to, is to use branch prediction. Basically, it's saying, I'm going to try and do my best to guess if it's taken or not taken. And if it's incorrect, then I'm going to flush the pipeline, aka render all the instructions that you just loaded completely useless. So in 61C, usually the branch prediction that you'll have is the problem will tell you the branch is taken, the branch is not taken. So that's the most simplistic way that you can do it. Basically say the branch is always taken or the branch is never taken. And it's only after execute that we can say, okay, was I wrong or was I right? And so you can say like it's kind of simple because all you have to do is kind of hardwire it to be one way, but it's also often wrong because like you're not always going to have a branch that's taken or you're not always going to have a branch that's not taken, right? Otherwise, it kind of defeats the purpose of a branch. Yeah. Yes. Yeah. So branch prediction, I'm going to say soft yes because that's all I'm aware of. I do not do branch prediction research, although that's really, really cool. Sorry, like branch prediction research is like insanely cool because they literally like take instructions, like the really advanced types, like they take instructions that you have previously executed or might in the future, and then like try to calculate whether or not you'll take a new branch based off of the previous branching behavior. So it's really cool, but that's really complicated, and we don't cover that in this class. But so yeah, in at least in 61C, the only tree that you need to be aware of is if a problem says the branch is always taken or the branch is never taken. And then so you base off your pipeline based off of that. No, so oh, you mean for the project? So you won't have to make that decision. So the question will tell you like the branch is always taken. And then in that case, if it's always taken, then you know, okay, it's always going to like load the label stuff first. If you're wrong, then you'll flush the pipeline and then load like the next instruction, subsequent instructions. But if you're right, you have the pipeline loaded. Like on the converse side, if it's the prediction is the branch is never taken, then what you're going to do is, okay, execution, you're going to load or fetch this instruction, and then you're going to fetch this next instruction until the end of execute stage, which is then when you decide, oh, do I need to flush or not? So yeah, it's just 2 different predefined behaviors. Mm-hmm. What do you mean by throw an error? Mm-hmm. Oh, okay. Yeah, so like I guess in practice, like in project 2, like I don't actually know what the behavior of the branch predictor, if there is that one. Like the whole point of a branch predictor, I guess, is for optimization, which is not the point of project 2. So that's why we don't really talk about it. I actually don't know if there is a branch predictor at all, or if we just kind of ignore it. But yeah, so like even if like you notice like in like a section of code, you're like, oh wait, like we should not branch, but then the question says like assume always branch. Basically what that means is unless you have like say the register values, what basically that means is it's saying, okay, the branch predictor is saying that you will always branch, and if you don't, then you have to clear the pipeline and reload the instructions. So I'll show you an example of that in the worksheet or when we get to there. Okay, I'm gonna move on just for the sake of time, and I think that's actually it for the presentation part. Do we want to like a small break before we head into the worksheet? Are we okay? Yes, okay. We'll reconvene in 4-ish minutes. So take a break, do whatever you would like. Okay, we're gonna get started again just in the interest of time. So I guess just to really kind of hit the point home. I'm gonna give everyone maybe like 3 minutes to go through or 2 minutes to go through 1.1 through 1.4. So these are just like simple true false ones. Just like give it your best shot, see how it feels, and we're gonna go through the answers a bit quicker to get a general sense of like how people are feeling about all of this. The forwarding is what we were talking about with like passing the output of say from execute or memory to the start of execute in the next stage. Yeah. So it's also called bypassing in some places. So if you look at online resources, they'll use both terms. Okay, cool. We're gonna kind of go through the answers now. So for each of these, for first one, if we have, okay, pipelining the CPU data path results in instructions being executed with higher latency and higher throughput. True or false, usually. Fight it out now. Yeah, do okay, so yeah, the point of so just to really quickly define these two terms. So latency basically means like the time it takes or time taken to execute an instruction. And then throughput, so and then throughput is a number of instructions through a sort of, I guess everything kind of has to do with everything, but yes, sort of in a second. And so a number of instructions that go through the pipeline in and say like n units of time. And I'm really unspecific with how many units of time and what the units of time are because like the throughput can be defined in different ways. Like maybe how many instructions go through per second or how many through like a nanosecond or something like that. But basically the whole idea is so latency it's a higher latency, aka it takes longer to execute every instruction because we have to wait for all the other instructions to be done before we can pass through that part. So in theory, like for example, if we have an add instruction that very obviously doesn't need the memory section, technically speaking, they could be done with it and kind of like bypass it in a regular data path. But so like the amount of latency that it would take for that instruction. But because if we have like a load word right before that, it has to wait until the previous like load word has finished and it has to kind of sit in the memory stage for the load word to write back before it can move on. And so that's what causes the higher latency per instruction. So it has to wait for all the other instructions maximum times as well. And then the throughput increases because that's the whole point of pipelining basically. So in say like 5 clock cycles, we can in theory, or so okay, in one major clock cycle, like for a data path or for a regular unpipelined data path, we can only pass through one instruction. But in theory, in a fully pipelined data path, we can have 5 instructions pass through in maybe that same amount of time. Highly unlikely, but in theory, that's possible. But what we do know is that you'll have more than one instruction that passes through in that certain amount of time. So that's why both of these will increase. Does that make sense? Okay. So for 1.2, without forwarding, data hazards will usually result in 3 stalls. True or false? I'm getting up to 2 thumbs up. Yeah, so this one is true. And the reason is because of the way that data hazards work and the way that the stages work. So if we have an instruction that has, okay, it's gone through IF, ID, execute, memory, and write back. So let's say we have, okay, let me actually move this over. So let's say we have an instruction at like what we had before, T0, T01. And so this next instruction, we don't really care what it is, but it actually just needs to rely on that. So we'll just use the example that we had earlier. So T2, T0 by 2. So because we both have this reliance on T, what needs to happen is, well, we can fetch our instruction on the next clock cycle. That's totally okay because fetching is just getting the next instruction. But we can't do instruction decode in this stage yet because we haven't written back yet. So we need to stall. And so then we just basically say, okay, we'll stay on instruction decode. We'll stay on instruction decode. We'll stay on instruction decode until we're done with the write back. And that's the next time that we can do execute and then mem stage and then write back. So we can see normally we would only need one instruction decode, but because of our stalls here, we have 3 extra ones. And so this counts as 3 stalls. Yeah, so data hazards will almost always be a result of like registers not being written to beforehand. I want to say like maybe memory, like if there's a store word and then there's a load word right after that, but you shouldn't need to access memory at the same time. So I think I'm confident in saying it's only registers. Yeah. Yeah.
When you question like this, you should say we don't have the ability to do double pumping.
Yeah, so the question will always specify like things that you can rely on. So if it doesn't specify there's any kind of forwarding, if it doesn't specify double pumping, etc., you can only assume that it has the most basic of a functionality, so you'll have to do all the stalls. So yeah, that's a good point that you make. If, for example, we had said like assume double pumping. So if it says assume double pumping, this would typically mean that you can do any combination of the 3 that we talked about. So read, write, or write, read. So the one that we're interested in here is the write, read, and that's almost always going to be the one that we're interested in. And so what can happen here is we'll actually get rid of 1 stall. So instead of that, we'll have 2 stalls. And the reason for that is because at this stage, the instruction decode can read from the register after the write back has already happened. So this can come first, and then this will come a second. And by that point, the register will be updated already. So we'll only need 2 stalls at that point with double pumping. Yeah. Does that make sense? Are there any questions? Okay. For question 3, so all data hazards can be resolved with forwarding. Thoughts? Okay, yeah, so it is false. And the reason is because forwarding refers to basically like being resolved means that you can properly execute it in the very next instruction cycle. This is not the case with load word. And we talked about that earlier, and it's because we need that extra instruction in between. So even if there is forwarding, we'll still need a no-op or some other instruction inserted in between. So load word hazards must some kind of, oops, forgot that I stuffed over there, some kind of operation between load word and dependent instruction, even with forwarding. So for example, load word into, I'm using T0 a lot. So let's say A0 here, and then if we do, something like this, even if we have forwarding enabled, this will not work. But if we do have something like, for example, like if there's another instruction down here that's like register S0, T1 and T1, for example, or not T1, 2. If we have something like this, instead what we can do is reorder this. So we can do, okay, well, let's use a different color for this. So we can do load word T0, 0A, and then we can do before we do add. So in this case, with forwarding, I'm just going to mark this with forwarding. This will not work, but this will be okay. And that's because we have this extra instruction in between to shift it. So that's when we say like, oh, things are resolved completely, it means that in theory, this should work, or if it's resolved, then this should work, but it doesn't, so it's not resolved. Does that make sense? Okay. Load word hazards. Oh, here between. Yeah, sorry. Yeah. Yeah, the reason is because if we kind of look at, I forgot that this, you see that very, very faintly. Okay, let's make it a little darker. That kind of covers up the words. Which one's better? The first one's fine. Okay. So yeah, the reason that it works is because when we see, we have the TA0 kind of dependency right here and here. So yeah, typically what I like to do when trying to identify hazards is like highlight or underline or mark up like what registers are used. So I can see like, okay, is there a dependency later? So we can see, yeah, that there, yes, is a dependency here. But even with forwarding, like we saw in the previous example, this will only be resolved, like this is loaded after mem stage. So we only know the value of that after mem. And so because we technically need this value during execution, so because we needed an execute and mem in two consecutive instructions will be happening at the same time, that won't actually work. So what we do is we reorder the instructions, or if we don't have another instruction we can insert, we would just insert a no-op, basically to push it one. So what this would actually look like is, let me add another page. So I'm just going to copy this over. I hope that this copied everything. See, this is why I like writing on tablets instead of like, you can't do this on a board. You have to rewrite everything. So what would happen here is, okay, we're going to write out the stages because writing out the stages usually helps a little. So here we have, okay, hello, there we go. IF, ID, execute, memory, and then write back. Good right now? Okay. So the next instruction that happens, so like, let's first assume that, I'm going to copy this. So I don't have to rewrite it later. But we're going to first assume that like just this line doesn't exist. This line exists afterwards. So we're going to put this here for now. So what happened here is, okay, we would fetch and then decode. But the problem here is we're relying on this value, right? So even if we do have forwarding going on, this kind of forwarding won't work because it happens at the same stage. So these happen at the same time. So instead, what the rational thing would be able to do is we would have to say, okay, we would need to either bump it by 1, 2, 3 until it's after the write back stage, in which case it's already been updated, or we could say, okay, well, we want the forwarded version. So forwarded version means that we could theoretically do execute here and then memory here, and then write back here. So we can see, okay, we need one no op here. And so we can now forward from memory to execute here. So these are two different ways that we could have this be executed. So if we compare this to our previous example though, so, and then, oh yeah, I'm gonna show what happens actually after this. So what happens after this is basically, okay, well, we can fetch this next instruction, but now we'll have to basically no op until the next stage changes. So we would have to do instruction fetch, instruction fetch, instruction fetch, instruction fetch, and then we can only decode right here, even though it has no dependency on anything else. And the reason is just because, well, we can't move into the next stage while the previous instruction is still actively occupying it. So we would have to have all of these no ops for this instruction as well. And they're technically like using the same no-op because it's repeating, it's repeating, it's repeating. It's not like we're inserting a new set, if that makes sense. So compared to what we had before, that actually did work. So this is the stall heavy method. So instead, what would happen in this next one would be, okay, well, this shift instruction doesn't rely on any of the values that we count on. So we can fetch it, we can decode, we can execute, and access memory, even though we don't need to, and then write back. This is totally okay. And then this next instruction that does have the dependency, we can do instruction fetch, instruction decode, and then, so we have two options. We can either stall if we don't have forwarding, so we would just do, okay, instruction decode, and then we would continue on with our lives. Or what we could do is the alternative option is, well, we could decode, but we could also technically execute and then do mem and then do write back like this with no stalling. And the reason is because at this point, the output from here is able to be forwarded to the next, I guess, time stage. And so at the next clock cycle, we can forward it and it'd be totally okay. But we couldn't have done that before because if we had done that over here, then what effectively would have happened without the no-op would be, let's see, okay, what color I haven't used. Let's use orange. So without that, we would have, okay, in theory, I'm just going to write it here. Instruction fetch, instruction decode, execute, memory, right back. And so that like just does not work because we have the output here and then we would have to pass it to the same time stage. So this does not happen. Does that make sense? So yes, and that's why we don't typically write assembly by hand because this is considered an optimization. And so I guess it really, like, it depends on the quality of the compiler. Like the widely distributed ones out there, yes, it'll do stuff like that. And that's why compilers are also very like machine specific, or like not machine specific, but rather like the code outputted is machine specific, because say if your system, like for whatever reason, doesn't have pipelining enabled, it can't like do all of these optimization and say, oh yeah, this is going to make things better, when in reality your system won't support it. Yeah, so then it'll like, so if it doesn't support it and it needs to do that, then your compiler will basically say, I'm going to insert no-ops because I know an instruction can't happen because of your hardware. Yeah, so that's why like the one of like not too cool compilers are still usually better than the best like assembly programmers. So, okay, going back to the last question, then stalling is the only way to resolve control hazards. How do we feel about that? Yes, so this is false. We have our lovely field of branch prediction out there that says no. Okay, so moving on to things, I'm going to skip over question 2 because it's conceptual. Question 3 is kind of timing stuff. I can come back to this at the end, but I think hazards and identifying them might be more useful. So we have a lot of kind of review on what structural data and control hazards all are. So I'm going to say, okay. So we're going to go through 4.1 and 4.2. And if you're done with that early, you feel free to head on to 4.3, but we're just basically going to walk through question 4 entirely. So I'll give you the next 5-ish minutes to work on that. Okay, so for question 4.1, based off of the title, like we know we're supposed to do forwarding, but let's just like kind of break down what the problem gives to us so that way we know what we can rely on. So we have most data hazards can be resolved by forwarding, which is when the result of the execute or memory stage is sent to the beginning. So the result, aka at the end of the execute or memory stage, is sent to the beginning of the execute stage for a following instruction to use. Notice here that we don't mention double thumping to any extent, so we can't even assume that a register is able to be have 2 operations done on it by different instructions at a time. So that's completely out of the picture. So looking through what we have right here, The first thing that I like to do when kind of identifying these problems is first just like literally go through and annotate everything. So typically on an exam or a problem like homework problem, you'll have more than 3 lines because you can't really do much with 3 lines. But here we have 3 lines to practice. So the first thing to notice is, okay, do we have a destination register or not? So in the first instruction, we can see that we alter T0. And so because we do that, we have to now see, okay, do we access T0 as another source register later on? So the answer to that is yes, we do here and here. So if we had another instruction, for example, like and T0, like something like that, for example, this would not be a dependency because it's another destination register. And so the value of T0 is going to be updated by that instruction. So it's only if we have a destination register that's now later used as a source register, that's when we have a data hazard. So this is not a data hazard.
Not a data hazard because that's where it's being stored. Not
Yeah.
being used.
Yeah, so it's not being used as a kind of reading from it. So it has to be a write-read combination to be a data hazard. Yeah. But something that is of note is, for example, if we had like T0 and then not T0, like let's say S0 here, and we didn't have like any proper setup, what we can say, and we don't say that we have double pumping. What this is actually a structural hazard because, wait, sorry, I think I wrote the wrong thing. Yeah, no, never mind. Sorry. I was thinking about something completely different and it came out of, so let's ignore what I said right here. We'll pretend I didn't say it. Yes, okay. But basically like the idea of a structural hazard is say like it wouldn't exist here necessarily, but say if we had like a read happening before a write, then it wouldn't happen, or it wouldn't be a sorry, what's it called? It wouldn't be necessarily a data hazard, but it would be a structural hazard. So ignore what I said previously about T0 being right there. But yeah, now that we have this, we know that we have that dependency, and then you see that we can write to S0. I can't see that at all, okay. We write to S0 right here, but we don't rely on S0 later on, so that's not a data hazard. And then the last thing that we write to eventually is A0. But we also do not rely on that at any point. So that is no longer, that's not considered to be a data hazard. Does that make sense, Black? Oh, this? Yeah, this is not a data hazard.
That's not.
Mhm. Yeah, so the reason is because T0 gets updated. It's not being depended on later as a read. So it's a write that updates some register and then a read later on from that same register that hasn't necessarily been updated. That's what a data hazard is. Mhm. Yeah.
Okay, so A0 would not be a hazard.
Yeah. Yeah, so in this case, then we only have 2 data hazards, so 2. And so the data hazards that we have are between line 1 and 2, and then 1 and 3. Yeah, T0, T0 from add I and then add I and a shift left or set less than immediate unsigned. Just line 3. But yeah. Yeah, that's a great question. So that's what something that we can solve by forwarding, right? So the first could be resolved by forwarding the result of execute from right here to the start of execute right here. Do we see how that fixes things? Okay, I love the honesty. But basically the reason that that can be fixed is because we have the output of execute, which, so the output, let me change to a smaller one. So T0 here is going to be set equal to A0 minus 1, right? So we know that that happens in the ALU. So this is in the ALU, and that happens by the end of execute. And this is the value that we want in the next stage. So in clock cycle 4. So write back only like actually writes it to the register, which is useful for later on because we don't want to depend on forwarding for every single thing. But this is kind of a good quick fix, right? So later on, that might actually like be useful for other T0 as source registers. But right now, because we haven't hit the write back stage yet, T0 has not been updated. So now if we do the forwarding, this T0, even though we've decoded it right here, and T0, let's say includes, I don't know, or like has some random address or just some value garbage that we don't care about, if we forward it and we know that we've kind of accomplished forwarding, then we don't care what like T0 is at this point or by the end of decode, and we can say, okay, well, we're just going to ignore this value or the stuff that T0 is decoded to be and say, I'm going to use the T0 value that comes from the previous execute stage from this line here. Huh? So it's not. So it's what T0 would eventually be. So it's A0 minus 1, the value there. Yeah, so it's not like the value of T0, it's what T0 will eventually be. So it's just the output of whatever instruction is happening. So A0 minus 1 here. So that's what forwarding accomplishes here. So like, let's say, okay, so between 1 and 2, we'll say, okay, like the start of execute uses T0's future value. So AKA A0 minus 1 from ALU output. Does that make sense? Where's what pointer? That just means it's kind of like a symbol just to show like forwarding in hardware. Like you can't like just show all the logic that would happen on paper like that. So basically what it's saying is saying like, okay, between instructions 1 and 2, we're not going to rely on the original like the crossed out decode value of T0. And instead we're just going to substitute A0 minus 1 for the T0 dependency here. So instead, like what the instruction will look like is like it's effectively saying, and this is like not actual code, but this is just saying like this is what it's being calculated. And then, so because we got A0 minus 1 from the execute stage of here, so. Does that make sense? So do not take this to be, this is not an actual instruction. I'm going to label that. Huh? Risky? So yeah, so there's logic that goes into this, basically saying like, okay, if you depend on a certain register, like you'll see this kind of come into play during project 3, but like it's not saying, oh, forwarding will always happen or forwarding will never happen. It's just saying like conditionally, like this code like relies on this register, or like what the way that it does that is saying like, okay, at the decode value, like did the previous register like need to eventually, like is the previous destination register the same as like my current source register of the current instruction? If it's the same, then we know that we need to do forwarding. Otherwise, we know we can proceed normally. Does that make sense? Yeah. So yeah, it's not an always never. Yeah. Oh. Huh? Oh, instruction 1. It's the A0 minus 1 comes from the execution, end of execution stage of instruction 1. So my point here is like, this is not something that like comes from the compiler or anything. This is just like effectively like the values that we're looking at, because we're in this is like supposed to be T0's future value, but we don't have T0 yet. So we're going to just like substitute in the current calculation. Does that make sense? Okay. So in that case, I'm going to switch to a different color because it's gotten a little bit messy, but so that resolves the hazard between 1 and 2. So now we still have the data hazard between 1 and 3 to take care of. So does anyone want to venture a guess of how we can forward that? So it's not a trick question. Yeah, so we can just do something like this. So we start from here and then we make our way down here. So the forwarding path would be like that instead. And again, like it looks a bit wonky here, but the like hardware kind of example for that would be, okay, well, we know that for data hazards, we shouldn't be using, or if we don't want any data hazards, we shouldn't be using a destination register from say instruction 0 for the next 3 instructions. Because only after that will we be able to execute it. So for the next say 3 instructions that get passed in, so the next 3 previous the 3 stages that come after it, basically it's saying, okay, source registers, do you match any of the destination registers that we're trying to write to? If you match, then I want to forward, otherwise just keep going. So it's the same kind of logic, just applied to multiple instructions down the line.
What does that mean? Like registers, forwarding.
You can do that. So in theory, that would work. Just have like extra registers, but like part of the goal is to have like as simplistic as of hardware as possible, because like say for example, if you have a register, I'm gonna use blue for this, but say if we have a register between execute and memory where you just store the output of execute, then on the next clock cycle, whatever is being written to S2 is going to now overwrite that. So then you would need an additional register to make sure, okay, now this can stay there and I can use it. And that just kind of complicates things. Not to mention, then you'll have to like have a larger mux to be able to select like which input do I actually want. And so that really quickly like increases the complexity of the architecture. Okay, so imagine you're a hardware designer working on a CPU's forwarding control logic. How many instructions after that add-I instruction could be affected by data hazards created with this add-I instruction? So again, it's not a trick question. What do we think this is? So we answered this earlier. Yeah. So 3 instructions. And the reason is because it takes 3 cycles for us to get after the write back stage. We have 1, 2, and then 3. Okay, so I think, okay, I'm just gonna walk through 4.3 just in the interest of time, but stalls have to happen when forwarding can't happen. So almost always, like if you have like a whole setup with like pipeline logic, like sometimes you'll have a pipeline that says, okay, we don't have forwarding available, so how many stalls will you need? Sometimes you'll have forwarding available, but there's still problems that you can't resolve with forwarding alone. And at this point, we don't have double pumping, and we also don't have branch prediction just yet. And so if we look at this, okay, first things first, again, like S0, we know that that gets written to. We can see that there's an S0 here, but it's a source register, so that's okay. And it's from the same instruction as well. That felt really good. But we can see S0 does not get relied on at any point later on, so we can just kind of ignore it. And then the next add-I instruction again is T0. T0 seems to be having a bad day here. But we can see that it's a source register in the load word, and it's not used again later. And then we can see our final kind of update here is in T1, and then T1 gets used in instruction 4's add. So just from the get-go, how many data hazards do we have here? Yeah, so we have 2 data hazards between line 2 and 3, and then 3 and 4 with different registers. So one of these cannot be solved with forwarding. Before we like decide to like go, like let's assume everything is forwarded as it should be. So execute is linked to end of execute is linked to beginning of execute. End of mem is linked to the beginning of execute for certain instructions. Where do we need a no op? Yeah, okay. So we need a no op right here. And the reason is because we know that the load word for T1 would eventually will get stored into T1 will only be realized by the end of memory, but we need it at the beginning of execute for the next line. So this is not something that's possible. So we don't want that. And so because of that, now we need a no op. And so no op will cause, let's just cross out this whole one. This is wrong, or this is not valid rather. So instead what we'll have is, okay, no op means that we just shift our instruction fetch by 1. cycle. And then so we have instruction fetch, instruction decode, execute, memory, and then write back. And so now if we do forwarding, so now if we have the end of memory connected to the begin of execute, that solves 3 and 4's data hazards. And then similarly, for between 2 and 3, we can link end of execute to the beginning of the next execute. Are there any questions? Yeah, because load word, we have to access the data memory first before we actually get the output. Yeah, so idea like because it relies on just it relies on T1's value, but we already know that we're going to be doing some kind of forwarding. So in theory, yeah, if we didn't, so say if we didn't have, let's say we didn't have this purple. So instead what it would look like would be, okay, we would have ID, ID, ID. So now write back is done. So that's when we can do like that. This is the actual decode, and then we can hit execute. Oh yeah, so this is if we didn't forward from end of memory to the beginning of execute for 3 and 4. If we didn't have that forwarding, then only after the write back of this of instruction 3, then will the decode actually like quote unquote work. So we can see that we have this no op. So we started one later. So that's why we have this no op. And then we have these 2 no ops. So that comes out to be a total of 3 no ops if we didn't have that forwarding, as opposed to just 1 stall. Without to execute forwarding for 3 and 4, then we would need to stall 2 additional times as opposed to just 1. So it's 3 stalls versus 1. Does that make sense? Wait, sorry, could you clarify that? Yeah, so I would say like a way to like there are 2 category of things that like are available. So like first and foremost, like data hazards arise from instructions that like have a destination register. So like for example, a store word, it can never cause a data hazard. It can only be the like one of the like victims, I guess, of a data hazard because like you don't have a destination register, so it's never like writing back to the reg file. So if you have a destination register, it's inevitably probably going to cause some data hazard later on. It might not, but it has a good likelihood of doing so because it's writing back. And then out of all like the, I guess, destination registers, so there are 2 kinds. Like we have load word and then we have everything else. So load word kind of, you realize the result after memory because load word is like looking into memory and then pulling the result of that and then putting it in the register. And that can only happen after we've accessed memory, which happens in the mem stage. All the other instructions get their results after the ALU kind of does its thing, and that's in the execute stage. Does that help? Okay. Okay, so I'm just going to jump to the last part. Oh. Yeah, that's a great point. So that is just code restructuring, and yes, because this code is written non-efficiently. So what we have is, I think in the next one, So say you're the compiler and can reorder instructions to minimize data hazards while guaranteeing the same output. How can you fix the code? So I really hate that it's on a different page. I'm just gonna put it here because it's fine. So this is question 4.4. So like you said, because we can see that add I S0 S01 doesn't affect anything else because we can see S0 just never gets referred to later on. We can at the very least kind of restructure it to be between either 2 or 3 or 3 or 4. So where do we think it can go? So where do we want to put instruction 1? Yeah, so we can put it below 3. Because we know that because we have forwarding already, 2 and 3 now no longer have a data hazard, but because we still have the inevitable stall between 3 and 4, we're just going to shove an extra instruction in there. And in this case, like we had a no op before, but because we have a spare instruction, we can just move around kind of. We'll put that there instead. So the instruction order kind of becomes so add I S0 S0 1, and then oh wait, no, I literally just wrote the same thing. Add I T0 T0 4, and then load word T1 0 T0, and then this is where our moved instruction comes in. So add I S0 S0 1, and then we have our last instruction as T2 T1 X0. So we can see here that this is like effectively the same as having like a no op. But in this case, it's better than having a no op because we actually do something useful that our code wanted to do. Does that make sense? Okay. So we are technically 1 minute over. I guess I just want to really quickly, I guess, talk about, I think, question 3 while lab people come. So question 3 is a pretty standard question when it comes to like, how long do things kind of take to structure themselves? Oh, I realized I didn't actually scroll to question 3. Oh, it's done. Wait, what? Where is it? Oh, okay, the title is on this page. It's fine. Everything's fine. But this is kind of a typical question that's like, okay, well, what's the clock cycle of the data path? And then what's the clock cycle of the pipeline data path? And so a good way of kind of looking through this is, well, okay, if we don't actually pipeline anything, then we know that we don't need a bunch of extra registers. But if we do want to have the extra registers and thus pipeline things, then we need to actually incorporate them into our equation. So I'm just going to write out, so fastest clock cycle time for a pipeline data path. Okay, I'm going to do the single cycle data path first. So single cycle data path, we know that we need this time for the PC clock to queue, because remember, that's when we can actually read the PC value before it goes into IMEM. So this is the PC clock to queue time. And then we're going to add that to the IMEM read time because we don't write to IMEM, so it's always going to be a read. So that's going to be that. And then we're going to add that to a register file read. So we can see based off of the times that we have here, we care about this because we're reading from the reg file. So time of reg file read. And then we care about a tmux and then the ALU, because remember in the execute stage, we have the branch comparator, which is right here. We have the ALU, and then we have 2 muxes. But the muxes act in parallel, first of all. So we only need one of those muxes. And we know that mux plus ALU happens at the same time as branch comparators. So we want to do the max of mux plus ALU versus branch comparator. So we can see based off of the time, the ALU takes a fat amount of time, and 200 plus 25 is 225, which is greater than 75. And so in that case, we're going to eventually pick mux plus ALU for our equation. And then so after that, what we want to add is, okay, now we will care about the memory stage. So when we look at the memory stage, well, what do we actually have here? Well, we have a memory read here and then a memory write. So memory read actually takes longer than memory write. So we're going to have is okay, max of dmem read and then max versus dmem write. And so because we can see that dmem read takes longer, then we're going to choose that for our equation. And then our last part is our write back. So if you recall, what we have in the write back is we have a +4, or the +4 sorry, happens in the dmem stage. So actually this is like, and then the +4 adder. So that's very quick, but what we have in the write back stage is we have our mux that's choosing what value to output to the register value, or sorry, reg file. And we have our reg file setup time, because remember, we're writing back to the register file. And so in doing that, we're starting a new clock cycle. And so that needs to obey the reg file register setup time. So what we have here is we're going to have another mux. So this is the write back mux plus the reg file setup time. So if we were to like break this down into which ones correspond to which section, we can see that, okay, well, this is going to be instruction fetch. This is going to be decode. This is execute. This is mem. And then this is the write back. So when we look at this, this next question, I don't have time to go through it, but what you'll want to do is you'll want to calculate the critical path of each of these stages. So basically what will happen is, well, we know that we have a new start, kind of like we have a starting point and then an ending point. So for instruction fetch, we go from the PC register to the next register, right? Because we want to next register setup time. And then so all of the stuff after that are the pipeline registers between the pipeline registers. So we have the clock to queue time for that, and then the setup of the next pipeline register. So we're bookended by register, but everything in the middle that like actually counts as the timing components outside of the pipeline registers, kind of you can just like take them from this previous equation and then put them in the new instruction. So I think that's where we'll end here. I think we got to actually hit everything, but yeah, if you have any questions, feel free to post on Piazza or reach out.